at the end of yesterday's class, and I promised to get back to you on that, and so I'll do that now. And it was about the stream functions, which we said are not functions of time, but are functions of x and y, or we could write that as r and theta, right? We did a conversion there. And then as I was doing this, I said that the stream function is not a function of radius. And there was a good question about, well, why not? Why is it not a function of radius? Well, generally speaking, it can be. It can be a function of r and theta. We are concerned with flow right around the wellbore, okay? And flow around the wellbore is radial. And so what the streamlines look like is, flows coming in like this. So this is a producer. Okay, so you can kind of think of the streamlines right around the well that way. And as you go around theta, clearly this streamline is different from this one, is this one different from this one. They have different angles. But if you go in the r direction, right, this is, r, right, you're going out in r, the streamline's the same. So if, this is r and rw, the wellbore radius, and you go out further, it's the same streamline. Same thing over here. That this is a nice radial flow pattern. And so because of that, we say that what we did is we first derived these streamlines right around a single well, and for that, the stream function is independent of r, but is a function of theta. So we were able to neglect that portion. And then what we did is we used our superposition principle to combine these different solutions to get for multiple wells, and that includes the interference there. Okay, so I'm going to move on, and I'm going to talk about oil recovery and doing some oil recovery calculations. And I'm hopeful to get through this today so we can do some sort of example problem on Friday. So NP is the oil recovery, and remember, so the general formula is the displacement efficiency times the aerial sweep efficiency times the vertical sweep efficiency times the original oil saturation minus the residual oil saturation. This is NPD, and if we wanted to know NP, it's NPD times the pore volume. Well, we're talking about flow in 2D now, right? We were talking about flow in 1D, and when flow in 1D, EA was 1 and EI is 1. Now it's 2D, so there's no vertical component. We'll get to that next week. So this is 1. You'll have an initial oil saturation at SOR. ED is going to be calculated similar to what we did in 1D, but now we got to calculate EA. Okay, so this is 1D displacement efficiency. And this is 2D, or aerial sweep efficiency. All right. Now, EA, by definition, is the swept area divided by the total area. Okay, and I've tried to give it an analogy. I don't know if it's helpful or not, but my analogy is if you're trying to cut the grass, then your swept area is the percent of your lawn that you've contacted with your lawnmower, right? And so that changes with time probably. So at early times you don't have very much sweep, but as time goes on that increases. So this is the aerial sweep efficiency. It's going to be a function of the mobility ratio. I'm going to call it MS star, which I'll define in a moment. The dimensionless time, and our pattern of our wells. Okay. Now I think that I'm going to stick with the traditional kind of 1/4 5-spot pattern for doing this, but if you had a different pattern, it would be a little bit different. Okay, And remember what we're looking at here, right? So we have, this is our quarter 5 spot, so maybe we have an injector here, producer in this corner, right? It's not a full 5 spot, it's a quarter of a 5 spot. So normally this would be the center, but we're just looking at that quarter, and what happens is at early times, well, let me break this up into a few different regions. So we have prior to breakthrough, right? So, and to keep it simple, for now, let's just talk about the case where the initial water saturation is equal to the residual water saturation. So there's no water that's flowing. The initial water saturation is higher than the residual water saturation, it would be flowing, but let's stick to the simple case where SWI is equal to SWR. Prior to breakthrough, prior to water breakthrough, you're just producing oil because the water that's there is irreducible, it doesn't move. So you inject a barrel of water, you produce a barrel of oil, and this continues through breakthrough. Okay? And then you have a time that is after breakthrough, but before EA is equal to 100%. Right? So what you have is that you're injecting water, and you're getting these streamlines, and this first streamline is going to get there first. When that first streamline gets there, that's breakthrough. That's the first water droplet injected that reaches the producer well. As time goes on, you're going to increase your sweep efficiency. Okay. And this number will continue to increase until you get to 100%. Now, when you get to 100%, that doesn't mean you produced all the oil you can. This is just the breakthrough along these streamlines. If you want to think, the easiest way to think about this is each of these streamlines is a 1D displacement flood. Think about chapter 13, which we just covered on our test. We learned about 1D, and when breakthrough occurred, we didn't produce all the oil in the one-dimensional flood, right? We just started started producing some water as well, but we continue to produce oil really for theoretically forever, although the amount of oil we're producing slowly decreases. So it's the same idea here. Even when the flow along these streamlines reaches the producer well, and you get 100% sweep efficiency, so every edge of my 5-spot pattern has been produced, I still haven't produced all the oil. So this is after breakthrough, before 100% sweep efficiency, so you're producing oil and water in this period. And then you have a period that's after EA is equal to 1 or 100% until T is equal to infinity, technically, right? Okay, so technically you could produce oil forever, although it would be just, you waited long enough, it'd just be drops of oil and be mostly water. Of course, we would abandon our project before then. So we have to worry about these 3 periods. Period number 1 is pretty boring, okay? It's important. I call it boring. That's when we make most of our money because we're producing a lot of oil. And if SWI is equal to SWR, then we're producing 100% oil. If SWI is greater than SWR, then we're producing some water, but it's constant. It's equal to the fractional flow at that saturation. These two are more complicated and require a little bit more math. Okay, so let's talk about this. So we want an equation for EA. EA before breakthrough is really meaningless. Okay, what we care is about after breakthrough. And what people have done is done experiments to to develop some of these equations. And we'll use some of those. So this is the areal sweep efficiency. This is what we're trying to calculate. Is equal to the areal sweep efficiency of breakthrough plus a constant 0.274 times the ln of the water injected. So Wi is water injected in barrels. And this is the water injected at breakthrough, right? So you're going to be injecting water, injecting water, then you get to breakthrough, and then you'll continue to inject water beyond that. So if you look at this equation here, I'm going to we don't care, this is not applicable before breakthrough, we're not going to use it, we already talked about what happens there. But at breakthrough or after breakthrough, this is the equation. And if it was right at breakthrough, then Wi is equal to Wibt, the ln of 1 is 0, and then you're just left with this. So EABT is EA at breakthrough. So EA is the swept area divided by the total area when injected water first reaches the produced well, the producer well. Okay, and so this is the formula that we want. So we control how much water we inject, right? And so if I tell you we're injecting 100 barrels per day and we've injected for 100 days, then you would say, well, I've injected 10,000 barrels. So Wi would be 10,000 barrels of water. Clearly, we need to calculate how much water I need to inject at breakthrough and what the areal sweep efficiency is at breakthrough. This is the key equation for EA. We're also going to have to calculate ED later, right? Because NPD is ED times EA. EI is 1 because it's 2D, but we'll have to do that. So we have another correlation. So I should say we need the areal sweep efficiency at breakthrough. And what is that going to depend on? Well, let me go back. We talked about this slide last time. The sweep efficiency at breakthrough, and that would be this right here, is different depending on what the mobility ratio is. That sort of makes sense. If you've got a really viscous oil and you're injecting with water, then breakthrough is going to occur really quickly. The mobility ratio will be high. Water will find the producer well quickly. It'll kind of zip through there. But if the mobility ratio is low, for example, if you've got a very light, low viscosity oil and you inject water or a high viscosity water like polymer, then you have a low mobility ratio and the sweep efficiency is good at breakthrough. So clearly, the sweep efficiency at breakthrough is going to depend on the mobility ratio. Again, there's been some experiments that done to do that, and to keep things simple, equations have been fit to those experiments, like a regression analysis. These equations are on your slides. Okay, so that's the areal sweep efficiency at breakthrough. This is called the CGM correlation, or the Craig-Geffen-Morse correlation. So it was developed by them. They did some experiments, they fit a curve to it, and this fit the curve pretty good. this only applies at mobility ratios greater than about 0.2 or so, because if you put a really small number in there, then this number blows up and you get a value greater than 1, which of course doesn't make any sense. So you can't have a aerial sweep efficiency greater than 1. So, but as long as the mobility ratio is greater than about 0.2, then you can use it. If it's less than 0.2, then the aerial sweep efficiency at breakthrough is basically 1 anyway. So if you get a value greater than 1, then maybe it's equal to 1 if you have a low mobility ratio, or you made some sort of error there. Should be between 0 and 1. So this is the aerial sweep efficiency at breakthrough. Clearly what we need is this mobility ratio. How are we going to define that mobility ratio? It's going to be similar to how we've defined it in the past, which is going to be KRW or mu W plus KRO over mu O. This is evaluated at SWF bar. This is evaluated at SWI. Okay, so we're going to calculate M as bar, and then we can plug it into our EABT equation. A few comments about this. SWI is the initial water saturation. So what you do is you go to your relative permeability curves, and you calculate KRW and KRO at SWI. Viscosity of water and oil would be given. Now, if SWI is equal to SWR, the residual saturation, we know that KRW is 0. Okay, so that would go away. If SWI is greater than SWR, that wouldn't be true. Okay, well, what about this top term here? Well, this is evaluated at SWF bar, which is the average saturation behind the front. So I'll just make a plot here. If this is SW versus XD, we've got this. What we want is the average saturation in this region, so it's something in between there. Okay, this would be SWF bar, and how do we calculate it? Well, we've seen this formula before. SWF bar is equal to SWF plus 1 minus FWF divided by FWF prime. Okay, so we know how to do this. We go look at our fractional flow plots. We calculate our front saturation or front fractional flow and our derivative of fractional flow from the fractional flow curves. Okay, you're probably going to need the dimensionless time to calculate FWF prime. You use it to calculate SWF, you use it to calculate FWF, and then you get this. Then you can, at this saturation, you can calculate your relative permeability of water and oil, and you can calculate that. Okay, so that's how you get this. So once you get SWF bar, calculate your mobility ratio, plug your mobility ratio to get your aerial sweep efficiency at breakthrough, and then we could go over to here, and we plug that into there. Now we still need one more thing, which is the water injected at breakthrough. So let's figure out how to calculate that. So we need WIBT, which is the water injected at breakthrough. WIBT is equal to the pore volume times EABT, we just calculated EABT, times SWF bar minus SWI. We know all of that. Okay, so this is the water injected at breakthrough. So this term in parentheses is the pore volume swept, right? Because it's the pore volume times what's swept. And then even in the swept area, we don't inject everything along that streamline. We don't inject everything in 1D. We know that we leave some oil behind when we do that. So this term in parentheses is the change in average water saturation that occurs along those streamlines. So SWI was the initial saturation, SWF bar was what we just calculated, and that's that average saturation behind the saturation front, and we're looking at breakthrough, so it's gotten through there. Okay, so this is the amount of water, and this is going to be in barrels, the amount of water we've injected at breakthrough. So we got everything we need to get EA. We've got WIBT. We learned how to calculate EABT. And then we go in here and we get EA. But as I mentioned, the oil recovery is the dimensionless oil recovery times the pore volume. Dimensionless oil recovery is ED times EEA times SOI minus SOR. Okay, presumably we know the initial oil saturation, the residual saturation. We just learned how to calculate EA, but we're also going to need to calculate the 1D displacement efficiency. That is going to work similarly in many ways to what we did in 1D displacement, right? I mean, that's what we did in 1D. We calculate EI. And so what we really want is to compute EI at this point. And we could do that before EA is equal to 1 and after EA is equal to 1. Okay, because remember, after breakthrough occurs, EA continues to increase to 100%. During that time, ED continues to change, continues to increase. And then, at some point, you'll get to an areal sweep efficiency of 100%. But that doesn't mean we've produced all the oil we can. ED will continue to increase beyond that. So we're going to kind of break it up into these two regions. Okay, so one thing we need is a dimensionless time. We called that TD before. I'm going to call it a different variable. I'm going to do that because that's what most of the textbooks and literatures do. This is a dimensionless time. I'm using the letter Q now. And at breakthrough time, so this is basically the dimensionless time for breakthrough, which is the amount of water injected at breakthrough divided by the pore volume divided by EABT, which from this formula, you divide by VP EABT, it's just equal to SWF bar minus SWI. Okay, so that's easy to calculate. You can calculate your dimensionless time at breakthrough. So I'll call this dimensionless And if we go back to our formula for EA, I'm talking about this formula right here. This is the equation for areal sweep efficiency. We could use it to determine how much water we need to inject in order to get to 100% areal sweep efficiency. So when EA is equal to 1, that would tell us how much water we inject at that sweep efficiency. So what I can do is I can say EA is equal to 1, which is equal to EA at breakthrough, which we know, plus 0.274 times the water injected at 100% sweep efficiency. I'll call that WI 100 divided by WI breakthrough. And then you could solve for WI 100. So I'll say that WI 100 is equal to WI at breakthrough, E to the 1 minus EABT divided by 0.274. And we know everything in there. We've already calculated how much water is required at breakthrough. We know the areal sweep efficiency at breakthrough. That'll be a number less than 1. Okay, and you plug in this formula and you figure out how much water you need to inject to get 100% sweep efficiency, areal sweep efficiency. Okay, so that's useful. And what it's and that's going to be useful for this region. We're going to split up. We're going to split this up into 1 EABT until EA is equal to 1, or you can think of it as WIBT to WI 100. And then we're going to, okay, and remember what we're trying to do is we're really trying to calculate ED during that time. And then we're going to look at EA is equal to 1 to infinity, right? And we'll calculate ED then. Okay, so we're going to break it up into 2 different periods because different things are happening. During this time, ED is increasing, but so is EA, and more streamlines are reaching the producer well. Once we have 100% sweep efficiency, all the streamlines have reached the producer well, and we're just increasing ED along those streamlines. In both cases, we know that EI is the average saturation of the producer well minus SWI, which is equal to SWP, that's the water saturation at the producer well, minus SWI plus 1 minus FWP over FWP prime. This is a formula you used on the exam and all in chapter 13. In fact, I think that this was the very last question. So the last question of number 4, you had to use this equation. SWI is given, you know that, but you need to calculate the water saturation of the producer well, the fractional flow of the producer well, and the derivative of the fractional flow of the producer well. All those things change with time. So you need to know the time, or really what you need to know is the dimensionless time. So what you need is FWP, the derivative is 1 over dimensionless time, and we're calling this as QI star. Okay, we called it TD before in 1 dimension, and we're calling it QI star in 2 dimensions. but this is the dimensionless time. You take the reciprocal, that gives you the derivative of the fractional flow. You go to your derivative of the fractional flow curve. You can calculate SWP from that. From SWP, you get FWP, and from that, you get EI. That's it. That gives you EI. You multiply it by EA, which we've already calculated. That gives you the dimensionless oil recovery. Multiply it by the pore volume, that gives you the oil recovery in barrels. That's, of course, what we care about as reservoir engineers. There's one last trick here. How do I calculate the dimensionless time? Okay, it's not quite as simple as what it was in 1D. I already told you how to calculate the dimensionless time at breakthrough, right? Let's see if I can find that. So I gave you the dimensionless time at breakthrough, but we're interested in times greater than breakthrough. Specifically from breakthrough to EA is equal to 1, and then from EA is equal to 1 to infinity. And those are going to be two different formulas. So from WIBT, from breakthrough to 100% sweep efficiency during that period of time, the formula is QI star over QI star at breakthrough is equal to 1 plus A1 e to the minus A1 We've seen EI before. That's the exponential integral. It's just a function. Okay, I know it's not one that we're used to using all the time. It's not something that's readily available on some simple scientific calculators, but it's just a function like sine or cosine or any other function that we know. And we've used it before. Okay, and A1 is going to be 3.65 EA BT, and A2 is going to be A1 plus the ln of WI divided by WI BT. So you know EA BT, you know WI BT, so you can calculate A1 and A2, plug it in, and then you just evaluate this function using Excel or Python, or maybe some fancy calculators can do it as well. Well, what I'm going to try to do is see if I can make a nice plot for you for this that you can use. We'll see about that. But this is only up until 100% breakthrough. For WI is greater than WI 100, it's a little simpler. Well, in some ways. So QI star is equal to QI star 100 plus WI minus WI 100 over VP. So WI 100 we calculated previously. That's right here. QI star 100, well, that you need to come back to this equation, and you need to put in WI 100, calculate A2, plug it in, and then calculate QI star 100. Once you have that, you get your QI star right over here. So that is it. So from your QI star, you calculate your displacement efficiency, We talked about how you calculate your aerial sweep efficiency, and now you can calculate your total oil recovery as a function of time. Okay, well, you all have a wonderful rest of the day.